So we're in your chemistry book, chapter 11, section 4, and we're talking about metals, and we got to a metal that you may know all about, and that metal is iron. So on the periodic table, if you look here, here's the periodic table. What is iron? I hope you can recognize it here. If I put it here, close, you see where iron is? Fe is iron. So in the midst, we have iron, Fe. So remember, just remember, iron, Fe, okay? On your periodic table, a very important metal. So iron, here is an iron ore mined. You can see iron ore has been mined until ancient times. Iron is the fourth most abundant in the Earth's crust. Number 4 has 4.7%. And it's the second most abundant metal altogether. But it also is the cheapest. And it's used in forming steel. And steel is the most widely used as a metal alloy of iron. So we know iron and steel. So there are several types of ores, iron ores. And let me go ahead and put up my notes here. Can you see these types? So we have hematite, and that's iron oxide right here. So it's basically Fe2O3, and this is the most common, is the hematite. And then magnetite is F3, Fe3O4, a little different. And pyrite is FeCO3, which is carbonate, which actually is fool's gold. Fool's gold. So you have to know these ores here. I know what, and the most common be is the hematite. So fool's gold. And so going on, some characteristics. When you look at, looking at this hematite, it says right here, the major deposits of this ore are in the United States around Lake Superior in Minnesota, Wisconsin, and Michigan. The Mesabi Range in Minnesota is very famous for its deposits of iron ore. So that's in America, you can imagine. And here we go again as this mine, how an iron mine would look. Iron is soft, silvery white. You know, the iron in the midst as a pure metal, it would be that way. It is quick to react with oxygen, as we know. And this oxide, it causes rust. So you ever seen how iron rusts with oxygen? That's when it's reacting with oxygen. And it's reddish brown. Iron too, as ferrous oxide is kind of this reddish brown looking. So now let's talk about the iron furnace, blast furnace. How do we get this iron out of the minerals of the ground, out of the ore? And so since the Middle Ages, they've been doing this, even though it's quite complicated to get the iron out of the ore. So what process is this? Similar to the process of all metals getting melted, but iron specifically. So here, some pictures here. So let me put up my notes too, because I think I need to know the blast furnace. Oh, sorry. Well, I'll put my notes right afterwards when I'm going to go over them first. So this is a blast furnace, right? Quite a deal. Well, the blast furnace reduction is what we call the basic, even up to the ancient ways of way they basically would get the iron out of the ore. So the blast furnace reduction, iron rarely occurs in a free state, but in ancient times, they've learned to extract the ore with great effort. And this blast furnace was the primary reduction process to getting the iron out of the ore. and it consisted of a vertical heat-resistant column that was filled with the ore and fuel at the chemical reactions were to take place in the midst of this, and they would force this air into this furnace at pressure. The pressure nozzles at the bottom become very hot flame, and the liquid iron would collect at the bottom. And we have pig iron at the bottom and collect there. So in the past, blast furnace could be about 10 feet tall in the medieval times, and they'd have made of fireproof bricks and hand bellows. But now these blast furnace, look at this. They are 10 to 13 stories tall, from 30 to 45 feet diameter at the base. This is a blast furnace in operation here. Huge, a huge factory, right, with the furnace. And it has the steel outer shell with the heat, and 5,000 tons of iron are produced per day from the iron ore. So the top of it is iron. The top is iron ore, and most blast furnaces would use coke. What is coke? Coke is carbon. Just remember that. Coke is carbon. So coke and limestone. In the coke, the coal is heated in these huge ovens of carbon, and each ton of the iron is produced basically requires 1 3/4 tons of ore to go through this. So we're talking about 1 3/4 tons, almost 2 tons of ore going through, 1/2 ton of coke, which is carbon, and 1/2 ton of a limestone. The limestone, the reason they put the limestone is because it combines with and produces a slag. And actually they do use slag, and we'll show the chemical formula for that. The slag is used, you think that's just a byproduct, in a way it is, but they use that byproduct for different things. So the blast furnace in oxygen reacts with the coke, producing carbon monoxide at temperatures of 1,900 degrees centigrade. And so you'll have the carbon and the oxygen in the midst, bringing out the iron from the ore. So the molten iron sinks to the bottom. You can see here with the molten iron. So let's look here. We have the steel shell here. This heat-resistant bricks on the outside. Spreader, we have the iron ore, limestone, and coke added here. The exhaust gases are going to come up the top. And the slag is going to be formed here. The coke's going to be burning here. Iron ore is being reduced to take it out of the minerals. And here's the oxygen. They're going to bring oxygen, pure oxygen, in here for the combination. And then the slag, which is with limestone and stuff, but the slag here. And then the very bottom will be the molten iron that we're going to collect here. Here it's coming out this little duct, and the molten iron is being collected. And this is what we're going to use as iron. And then the slag is being collected here, and that'll be used as slag too. So you see that picture? The blast furnace. And so let's go look here. I just wanted to show you the formula. So here's the coke. Carbon is C, right? Plus oxygen, and you get carbon dioxide and heat. And this is in the furnace heating up in the midst using carbon. The carbon is combining with iron oxide here, and then at that high temperature, the iron is being set free, and carbon dioxide is forming instead, taking away the oxygen to carbon dioxide. So that's the formula. And the limestone with the slag down here at the bottom, here's the calcium. Remember, calcium carbonates limestone in the midst. Then it is separated from the calcium, oxygen, and the carbon dioxide in the midst. So it's decomposing too, but in the midst producing the rest. What's left over would be the slag. So CaO, which is lime, reacts with the sand and silicate to form molten calcium silicate right here. So, and calcium silicate mixes with other impurities to form the slag. So that's how we get the slag. The molten iron, of course, is taken out at the bottom. We already went over all that. So another type of not the blast furnace, but another type of reduction to obtain pure iron is called direct iron reduction. And the direct iron reduction, the reason they have this direct iron reduction because coke, which is carbon, was put out as putting out into the atmosphere carbon, you know, so the environmentalists said, okay, we can't do this. We're not going to be able to use this coke. So instead they started using natural gas, which is methane. And in doing that, reducing iron to what's called sponge iron. This sponge iron. So here's the formula of reducing this to get the sponge iron. But sponge iron is you can't just use sponge iron for regular iron. You're going to have to take that sponge iron and turn it into steel. So it's used to manufacture steel. So with the sponge iron. So the reason there, it's only for making steel, the natural gases, and they don't want to use the coke anymore. They don't want to use carbon, putting too much carbon into the air. So, and later they add flux later to the steel for the impurity. So we're going to go over steel too, but basically saying the direct iron reduction is another way so that we don't have to use the carbon coke, right? So let's talk about steel refining now. So we'll go over and I'll show you the picture. So steel refining, there are pig iron, which is the cast iron, like if you wanted to have a cast iron pan to cook in with a lot of iron. Well, that's called pig iron or cast iron. And that is very brittle. And so they wanted to basically take making it into an alloy. An alloy would be something added, another element, or I should say element or metal or stuff added as an alloy. Well, carbon. So basically, first of all, taking carbon and adding it to iron, and that's what we were doing in those in the heaters. Now, basically, I'll show you how they're doing it with steel, but going into carbon steels with the carbon and the iron, less than 0.2%, and making it low-grade steel type with wires and increasing the carbon a little bit more, strengthens and makes it into a steel, which is very not brittle anymore. It's very hard, you know. So a high carbon steel would be like 0.6% to 1.5%. So that's one of those types of steel. And then there's a medium steel here, and high carbon, from high carbon to medium steel being 0.2% to 6%. So we have medium steel and high carbon steel. So we're talking about carbon being mixed here. And then on to alloy steels. What's alloy steel? It's another type of metal alloy that's added to iron. And in doing this, a low alloy would be 1% to 5%. A high alloy would be up to 5% or more. One alloy would be like stainless steel. Stainless steel has 14% to 18% chromium. Or nickel, as you add to stainless steel, which would be 7% to 9%. And the stainless steel are really good for your kitchen cutlery, you know, so they don't rust, right? Hospital equipment, tools, firearms, boat equipment, all these things for a stainless steel. So properties of alloy steels. Vanadium is a springless tensile strength. It's an alloy. Manganese is a wear-resistant hardness to iron. Chromium, of course, is hardness and it's corrosion resistance like stainless steel. Nickel, very tough. Tungsten and molybdenum are basically heat resistant and tough. So these are alloys of steel. The basic alloy of steel would be carbon though. So, okay, the steel refiner, I'm going to show a picture. Here we go. So again, here we have the basic oxygen furnace that's used in steel. The basic type of steel processing is oxygen processing. And in the midst of oxygen processing, basic oxygen process is refining this pig iron to steel. And they put this in the chamber, as you see there, with these bricks of magnesium and calcium bricks oxide outside. And it can hold over 300 or more tons. Right here. Here's a big electric arc furnace, but this is the one I'm talking about right now. This basic oxygen furnace. You can see where the molten metal at the bottom, and again the slag, and this is the tap hold coming out. And we have up here the flux charge, the waste gases, the steel shelled line on the outside. You can see in the midst the basic oxygen furnace. So. The molten iron in there is agitated with this oxygen blast that comes in at 1,650 degrees. So, and the reactions are very rapid. It takes like a half an hour there, and lime is added for the slag, and the sample steel is drawn off and then analyzed to see if it's just what they want. And then on to another type. This is the basic oxygen furnace. And this is the electric arc furnace. Look how huge that is. 60% of steel production in the United States is the electric arc. And as you can see here, that it goes with higher temperatures are possible than the oxygen process. And it's effective removal of impurities. This is used a lot in recycling steel. So. Okay, this last part, annealing, hardening, and tempering, we're going to go over that. I'll go over my notes in that. Let's see. So let's go over, this is a case hardened steel. We'll see that. But let's go over, I'm going to go over my notes in the midst of. Okay, first we had the blast furnace there, as you can see. In my notes, the oxygen reacts with the coke, remember? The coke carbon. And this molten iron sinks to the bottom, as we saw. Limestone liquid decomposes into slag, and it floats up to the top. And the molten iron to the bottom, and that's where we get the pig iron, right? Onto the direct iron reduction, because they don't want them to use coke anymore, which coke is basically putting too much carbon pollution in. So they went to an alternative with natural gas. And so now this reduces iron to the sponge iron, which only can be used for steel though, not for plain elemental iron. And so this gas goes to carbon monoxide and hydrogen, and later adding flux for the steel. Onto the steel refining here. We talked about the steel alloy of irons. There's the carbon alloy, right? Carbon steels. And then onto the alloys of chromium and nickel, very popular. The basic oxygen process was the oxygen blast furnace, which I showed a picture of. And this is where pig iron is turned to steel. The oxygen oxidized the impurities and limes added. I showed a picture of that. And of course, that electric arc furnace for steel refining at real high temperatures, and basically it can be used, or steel recycling for recycling steel. So, and now to, I want to go over really quick, kind of review of, not really review, I haven't really gone over it, but I was going to go over my notes because if you read this whole thing, it's going to be a little confusing. So I put it together for you on steel. So as you look here, there's going to be 5 steps going through steel, basically bringing steel to the point where you'd want. Let's go back and see the picture, if there's a picture. Of course, those are the furnaces. Oh, I guess there's not a picture there. But this is many of the properties of steel, hardness, toughness, ductility, and malleability are determined as much by how the piece of steel is treated after it is made by the steel's alloy contact. So the properties of the steel may be improved in a number of ways. And these are the ways to improve on steel. So what are these ways? And I'm going to go over these. The first, there's actually 5 of them. The first is annealing. And this is when the steel is heated to 700 to 800 degrees, which is, high temperature, but not as high as the steel has gone through. And so for several hours, and then it's slowly cooled, and the iron atoms then start reorienting themselves and relaxing, and the steel becomes very soft and workable. This is called annealing. Now hardening has nothing to do with temperature. Hardening is basically working the steel in what form you want it. So cold working was where they would bend the steel and hammer the steel at these low temperatures and work into what kind of steel object you wanted it to look like. And then the cold forging, these are all cold because it's not heat. The cold forging, they take this giant stamp hammer and start stamping the steel down. That would be cold forging. And onto cold rolling, they would roll it into these big sheets and then squash them down, basically into thin sheets. And then the drawing, sometimes they pull them through a small hole to make them more, malleable or ductile. So that's hardening. The next would be quenching. And so quenching, basically it would be heated to a red hot degrees. This is a high degrees, it's 1,340 degrees. And this breaking it, and then the carbon is in it. Then the carbon dissolves there, and they dip it in cool water and make it into a stronger type of steel. This is quenching. And then tempering to make it less brittle, as iron is pretty brittle. It's similar to annealing. After quenching the heat to a moderate heat, brief heating little periods leaves the stress, and then the metal becomes resistant. So annealing and tempering are quite alike. And then on to surface hardening. You see surface hardening is at temperatures again at temperatures of 900 degrees. The carbon-rich environment there diffuses into the hard surface, and later on, so then it forms a case with carbon and nitrogen on this case. And this, the interior cools more slowly and it puts together tough steel. So let's go over it. The 5 different ways to do this: annealing, hardening, annealing at high temperatures, hardening, quenching, tempering, and surface hardening. Okay, and that's all in your book. So here's a picture of a case hardened steel. So this is basically how you have steel. What do you want to make the steel into? And so that's what it's doing. So it's tough and resilient inner layer, and the hardened surface on the out. This is the picture of a case hardened steel, and that would be the surface hardening. So again, we have annealing, hardening, quenching, all these things onto tempering. So if I say what's quenching is heated at 1,340 degrees, and where the carbon is quenching it by dissolving in the midst of it. So It's kind of hard to describe, but you can read it over. So let's go over some of these questions here and we'll finish up. I'm not going to go over every question. Some of the things I already went over. I don't want to repeat myself. So, number 1, tell by equations how pig iron is produced in the blast. Well, we'll go back to those equations, which have to do with carbon and oxygen, and bringing that carbon and oxygen in with the iron oxide and bringing that out. So you can look at the equations back there. We went over them already. Number 2, give equations for the producing of slag. Of course, slag is going to be calcium carbonate, and how that slag, in fact, I wrote them here, so if you want to look here, you can stop, and there you go. For slag, my little chicken scratch there. List 2 uses for slag. Well, slag can be used, I didn't go over that. Slag can be used for cinder block, concrete, asphalt, railroad support ties, also insulation. So like if we have insulation that's put in your houses, can be taken from slag. So they use every part. It's not they take out the iron ore and they're using the slag for concrete, asphalt, ties, and insulation. So how does direct iron reduction differ from blast furnace? Blast furnace uses coke, which is carbon. And because a lot of environmentalists don't want us to use so much carbon, right? They have basically put together, taken out the carbon there in the midst and using natural gas instead. So, describe basic oxygen process for iron refining. So the basic oxygen process is the pig iron is refined to steel in these supersonic blasts of oxygen in the steel for only a half an hour. So very important. How does the electric arc process differ from the basic oxygen? The electric arc process is steel recycling, remember? So, and it uses electric arc between these giant carbon electrodes for cold scrap metal, and using basically as a recycling steel. And basically the electric arc process is at much higher temperature. So number 7, name 3 ways to increase the hardness of a piece of steel. So 3 ways. Well, we went through those ways, basically going through them again. Annealing, hardening, quenching, tempering, surface hardening. But hardening in itself, you can have cold working, where you bend and hammer it, cold forging, where the giant hammer stamp comes down, or cold rolling it into sheets. So those are the hardness. Cold rolling, cold foraging, and what did I say? Cold cold rolling, cold foraging are the 2 with the stamping. And the first one was cold working. So what process can be used to make a piece of quenched steel less brittle? So process to make a piece of quenched steel less brittle is tempering. That's what we do, the process of tempering. Tempering. This makes it less brittle. Oh, no, quenching, tempering. To make it less brittle is tempering. Okay, that's it.